Section 1.2, Scientific Approach to Knowledge. We can approach problems in different ways. We can take, just wild guesses, or we can approach things in a more scientific way. And so we're going to learn about a more scientific way to approach problems. And this is empirical. And the word empirical means that it's based on observation and experiment. This is not like the Greek philosophers that sat around and thought about things. So, well, I think that this must be how it is. Modern science is based on experiment and observation. It's empirical. We have an idea and then we do something to test it. So what we call the scientific method is a process for understanding nature. And it's not a set in stone, do this, 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 this. It's a general approach. So we understand nature by observing it, by conducting experiments to test our ideas. So, let's see here. So the important ideas here are hypothesis, experiment, observation. So we observe, we look, we measure, we write stuff down, we observe something. Then we formulate a hypothesis. What do we think this means? Then we test it with an experiment. And from the results of the testing, we can form laws and theories. So those are the basic ideas of the scientific method. Observations are also known as data. They're descriptions about the characteristics of or the behavior of nature. They could be something quantitative, like the mass or the length or the temperature of something. They can be qualitative, the color, the smell. Is it soft? Is it hard? Those sorts of things. So just a little historical example that we're going to follow a little bit. Antoine Lavoisier lived back in the 1700s. He was French. He noticed that there was no change in the total mass of material when he burned something in a container. If he burned it in a sealed container, what was left weighed exactly the same as what it weighed before. And this was kind of surprising, because if you think about burning a log in the fireplace, a big log, it's heavy, you stick it in there, you burn it, what's left afterwards? Ash. Does the ash weigh the same as the log? No, it doesn't. Well, Lavoisier did something similar to this in a closed container. He burned it. He weighed it before and after, and much to his surprise, it weighed the same. What's up with that? Well, that's an observation. Okay? Observations often lead us to formulate a hypothesis. A hypothesis is a tentative interpretation or explanation of what we've seen. It's kind of like a guess. It's like, well, look at that. Well, I think this is what's happening. You try to figure out why it's happening. So Lavoisier tried to explain his observation by hypothesizing that when a substance burns, it combines with a component of air. That's what he thought. Well, when it burns, it must combine with something in the air, and that's why it still weighs the same. An important characteristic of a good hypothesis is that it is falsifiable, meaning that you can test it. If you can't test it, it doesn't do much good. You know, if your hypothesis involves aliens coming down and injecting stuff into your container, how are you going to test that? If it involves, invisible things, how are you going to test it? It has to be testable, has to be falsifiable. So we test these experiments, we test the hypotheses with experiments. And experiments are highly controlled. We try to control all the variables. We make sure the temperature is the same, and we control the volume, and we control all these different things. So we control the variables, and then we generate observations. So we take that hypothesis, and we test it by doing an experiment. So I think this is what's going on, and I'm going to test it this way. So I'm going to, the whole idea of the burning thing in the container is nice, but I'll give you a less scientific sounding experiment problem. Okay, so I have 5 sons. So you can imagine the bathroom that they share. The floor is not very clean. So there's a puddle of liquid on the floor by the toilet. So that's an observation, right? And we can make more detailed observations. You can dip a white paper towel in it and lift it up and see, it's kind of a pale yellow. And you can smell it. Ew, right? So observations, those are observations. It wasn't there before, it's there now, those sorts of things. What might a hypothesis be? What is this stuff? It's most likely pee, right? It's unlikely that someone went and poured lemonade on the floor in the bathroom, although it's possible. But the smell doesn't smell like lemonade. So how did the pee come to be on the floor? Maybe it was the cat. Cats do that sometimes when they get mad. They pee on stuff. It's never happened at my house, so wait, yes it has. What's an experiment that we could do to figure out what's going on with the bathroom floor? We could clean it up, and then we could see if it comes back, right? So how could we test to see if how could we rule out it being one of the cats? We put the cats outside. Lock the cats outside. Pee shows up again. Was it a cat? Nope. So then we're thinking, okay, now we think it's one of the children, right? Must be one of the children. So, there's a variety of different experiments that we could perform. We could send all the children but one away and wait and see if it shows up again. And the person who's home when that happens must be the culprit, right? Although it could be more than one of them. We could set up cameras in the bathroom. That might be considered an invasion of privacy. But there's lots of different experiments that we could do to take our hypothesis that one of the children is missing the toilet and prove it to be incorrect or correct. So the results of the experiment may say, yes, that hypothesis seems reasonable, or may prove it to be wrong. Like we lock the cats out and we still get pee on the floor. Well, it's not the cats then. And so then we modify or discard the hypothesis. If the hypothesis is bad, sometimes we just throw it out. Other times we think, well, if we just tweak it a little bit based on the observations of that experiment, we can make it work. So after that level comes the idea of laws and theories. It's important to understand the difference. A scientific law is a brief statement that summarizes past observations, and it can be used to predict future ones. So an example is the law of conservation of mass. In a chemical reaction, matter is neither created nor destroyed. It's just a statement of what happens. It does not explain why this happens. The law of gravity. The law of gravity says that if I let go of this marker, what's it going to do? It's going to fall to the table. That's a prediction. Yep. It does that every semester. It's a prediction of future behavior, right? Does it tell us why that happens? No. A law just says This is what happens. We've seen it happen over and over again. We have no reason to believe that it will not continue to happen in the future. That's a scientific law. You cannot choose to violate laws, scientific laws. There are a lot of civil laws, right? There's a speed limit, traffic laws. You can choose to violate those. You cannot choose to violate scientific laws. If we have a hypothesis that becomes very well established, it may be elevated to the level of a scientific theory. A theory does explain why. John Dalton's atomic theory explained the law of conservation of mass. And it did so by proposing that matter is composed of small, indestructible particles called atoms, kind of like Lego bricks. And you can make this big Lego creation, and you can take it apart, and you can make it into something else, but all those little individual Lego bricks are the same. And so they're going to have the same mass. And that's why in a chemical reaction, the mass stays the same, because the individual atoms are not being destroyed. They're indestructible. And so that's an explanation of the law. That's a theory. Theory explains. So scientific theory is a model for the way nature is, and it tries to explain not merely what, but why. Scientists are generally pretty skeptical people, and if someone says, oh, we did this and this happened and this is why, we'll say, tell me what you did. I'm going to do it too because I don't quite believe you. I want to test it and make sure. So theories get validated by experiments in different labs, in different countries, over and over and over again. And so what's kind of unnerving to some people is that we cannot prove a theory to be correct. In science, we can't prove anything to be correct because some new observation or experiment, some new piece of technology always has a possibility to reveal a flaw in that theory. And we could go through many examples of the past of theories that everybody had said were true, but then we discover something new, and now, oh wait, that's not right anymore. So a theory cannot be proven correct. It can only be proven to be wrong. But the theories that we currently hold and are going to teach to you are ones that we have no known contradictions for. Nobody's figured out that they're wrong yet, and so we're going to go with them as being true. So here's kind of an overview. So we've got observations. That leads to a hypothesis. The hypothesis then is we're going to test it through experiments, and that may confirm the hypothesis, or it may I see. Confirm or revise. So if it confirms the hypothesis, great. If it says, no, that hypothesis was wrong, then we're either going to throw the hypothesis out or alter it. Laws also get tested. They get tested through experiment, and we confirm or revise the laws. And good hypotheses lead to theories, and those are also tested. So in everyday life, we sometimes say, well, that's just a theory. Well, in everyday life, that could be true, but we don't say just a theory in science, because in science, a theory is as close to truth as we have. So theories are very, very significant. Now, you might want to say, well, that's just a hypothesis, or that's just your own wild guess or your crazy idea. But a theory is very significant. It's also important to understand that science is not a set of steps that you go through to get a conclusion. It's like do A, B, C, and D, and then F will result. Science is messy. which is part of what makes it exciting. There's a lot of problems to solve and new places to go. And so it's a continual experimentation and testing of ideas and leading to new observations. Okay, quick example here. Which statement best explains the difference between a law and a theory? A law is truth, whereas a theory is a mere speculation. Is that a good description? No. A law summarizes a series of related observations, while a theory gives the underlying reasons for them. That sounds pretty good. C, a theory describes what nature does, a law describes why nature does it. No. This one would be fine if you switch theory and law. A law describes what, a theory explains why.